Hello everyone, let us today solve the problem linked list cycle 2. So, given the head of a linked list, return the node where the cycle begins. If there is no cycle, return a null. There is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, position pos is used to denote the index of the node that tail's next pointer is connected to. It is -1 if there is no cycle. Do not modify the linked list. Okay. So, this is our linked list, given linked list. We have to find from which node the cycle starts. So clearly we can see that from this node the cycle starts, right? Because this is a cycle, right? So when we start traversing from here and we finally come to this node, from this node we are going to fall into a cycle, right? So we have to return this node. So if we think about the naive approach, what are we going to do? We are going to use a hash set. Okay, how are we going to use a hash set? We are going to iterate over the list. Okay, and one by one we are going to put all these nodes into our hash set. Okay, so we are here, let's put 3, then we come to 2, let's put 2, then we come to here, let's put 0, then we come to -4, let's put -4. Then due to the cycle, -4's next node is this 2 again, right? Now we see that this 2, this node is already present in our hash set. So we have fallen into a cycle, we realize that we have fallen into a cycle, and this node 2 is going to be our answer, that from this node our cycle starts. Note that we are going to create a hash set in which we are going to put the node itself, right? Not the node values. Right? Why? Because let's say this is 2 and this node's value is also 2, so this will give us a wrong answer, right? The values are same, but if these two nodes are different nodes, their address is going to be different, right? So we have to put the whole node into our hash set in order to differentiate them, right? So this is the code for our naive approach. We initialize a hash set. Okay, then we initialize a node which points to head initially. Then we are going to move this node at each step. Okay, so while our node is not equals to null, we will see if this node is contained in the set or not. Okay, if it is not, then we will add that. Okay, we saw that, and we will move to the next node. We will keep doing this until we finally find that our current node is inside the set. What does that mean? It means that if we were at node say 2, we iterated, and we came back to it again, right? That's why it is already present, right? Because when we encountered it first time, we put it in the set. Now we have come back to it. That means our cycle starts from that node and we return. Okay, otherwise if there is no cycle, then we are going to finally exit this, right? Our iteration is going to stop while we reach null, and at the end we return null. So this is the simple approach. Okay, the time complexity is going to be a big O of n, right? Let's say n is the size of the list. Okay, and the space complexity is going to be a big O of n, because we are storing all the nodes in a hash set. Okay, now let's look at our second approach. We are going to make use of the fast and slow pointers. Okay, what are we going to do? We are going to initially place both of them at the head node. Okay, and we are going to move them in a particular way. Slow will move by one place, but fast will move by two places at each step. Okay, so what we are going to do, we are going to make them iterate over our list, and if there is a cycle, they are going to meet each other at some point of time. Why they are going to meet each other at some point of time? Let's say you have a racetrack. Okay, and you have two runners who start running from this point. Let's say one is running slowly and one is running very fast. Okay, so at some point of time, slow will slowly come, and but fast will moving so fast that he will ultimately meet his slow, right? Slow friend, slow opponent once again. Then slow will keep moving, then because he's fast he will again make another round and ultimately meet his friend, right? So if there is a cycle, then the fast and slow pointers are going to loop over the cycle. Okay, and they are going to meet each other at some point of time. So that's the simple logic. Okay, so we are going to find the meeting point. So let us now make them run over the race track. Okay, slow goes by one step, fast goes by two step. Fast comes here, then slow again goes by one step, fast comes by two step. Okay, okay, now slow moves by one step, fast moves by this here. Okay, then slow moves by one place, Okay, fast moves by two places, this and this, fast. Okay, now what did we see? Fast and slow are standing at the same position now. That means there is a cycle. They have finally met each other. Imagine there was no cycle. Then instead of this next pointer, this would be a null, right? Then fast would move out of the track, right? Race is finished, isn't it? This kind of a racetrack, starting line, finish line. So fast will move out. There is no cycle. They won't meet each other ever again, right? So that's the logic. They are going to meet each other. Okay. So we have found the meeting point. Now, what is the starting of our cycle? How are we going to find that? We are going to place a pointer here. Let's say it's n. Okay, node n. Okay. Now we are going to move this n by one position and our slow by one position. Okay. This will first come here, node, then slow will move here. Okay, slow. Then this will again come here, and this will come, slow will come here. Slow. So what do we see? Slow and this pointer which was at the head, they have met again. Okay. Now this meeting point is going to be our starting of our cycle. This is going to be our answer. Okay. So the algorithm is pretty clear. We are going to start with fast and slow. This moves by two places. This moves by one place. We are going to find the meeting point. Right. Now from the meeting point, start is going to move by one place, and from head a new node is going to move by one place. Okay. Now the meeting point of this slow and this new node head is going to be our starting of our cycle, starting node. Okay, so this is the algorithm. Now how is it making sense? Why does this work? Let's say our fast and slow pointer met here, right? Fast and slow pointer met here. Okay, now let us take that this distance is d1. Okay, and from the starting of our cycle to this distance, that is the meeting point, is d2. Okay, so how much distance did our slow pointer travel? It traveled a distance of d1 plus d2, right? Now how much did our fast pointer travel? Our fast pointer already traveled d1 and d2, right? By the time our slow pointer traveled d1 and d2, fast pointer already traveled this d1 and d2, and it made few circles around this circular racetrack, right? This cycle, isn't it? So let's say this the length of this cycle is, let's say, d3. Okay, d3, and let's say our fast pointer circled this cycle, let's say how many times? Let's say k times. Okay, so it becomes k into d3. Okay, now we know that whatever distance fast has traveled, it's twice the distance of our slow pointer, right? That is, whatever fast is traveling, it's two times the distance that our slow pointer has covered, right? Because we know that fast is traveling by taking two steps while slow is taking one step, right? So this is the situation. So what is this? 2 into d1 plus d2, right, which is equals to d1 plus d2 plus k into d3, right? Now 2 d1 plus d2 and d1 plus d2, 1 d1 plus d2 gets cancelled. Okay, this is what is remaining. d1 plus d2 equals to k into d3, that is d1 plus d2 is equals to number of times our fast pointer traveled, circled into the length of our cycle. Okay, now if we do this, d1 equals to k into d3 minus d2, we get this. Now what does this mean? What is d1? This is d1. And what is k into d3 minus d2? This is k into d3 minus d2. Okay, let's just ignore this k. Let's consider it one full cycle. Okay, d3 minus d2. Okay, so what is d3 minus d2? If this whole is d3, okay, and this is d2, then if we subtract this distance, we get this distance, right? Isn't it? So what does that mean? this d2 this d1 distance is equal to this d3 minus d2. That means, sorry, this from this area, okay, where our slow pointer is lying. So this distance and this distance is equal, right? What does that mean? If we have a pointer here, let's keep a pointer, let's say n, we put n, right? And this slow pointer here, they both are lying at an equal distance from the start of our cycle. This is what it means. Okay, so now if we move them by one step, if we move them by one step, move them by one step, move them by one step, they are going to finally meet because they are at equal distance, right? They take one step at each step and they are finally going to meet, and this is how we discover our starting of our cycle. So this is the kind of mathematical logic behind this approach. Okay, slow and fast pointers. So if we consider the time complexity, this is going to be a near around big O of n. Let's say, let's not make it more complex. Okay, big O of n, and our space complexity is going to be constant because we didn't use any extra space. Okay, so let us now look at the code. So now let's write the code. What is our task? To create two pointers, right? Slow and fast. Slow, that will be at head, also fast, that will be at head. Okay, let's call them S and F. Let's have a variable, boolean variable, has cycle equals to false. We are going to use it in future. Let's see how. While our fast is not null and our fast's next is also not null, we are going to move fast by two places. We are going to check if fast's upcoming nodes are null or not, because fast is moving faster, isn't it? Slow is lying behind. So fast is going to discover earlier, right, if a null node lies or not, right? Okay, and slow equals to slow dot next. In any case, if slow becomes equals to fast, then our hash cycle becomes true, right? Hash cycle, we saw that they finally meet each other at some point. Okay, and we break out. Now there can be two reasons of terminating this loop. Either our fast pointer encountered a null, that means we don't have a this thing, we don't have a cycle. Okay, let's say we have this node, then this node, and this node, this node, and this node. This is null, let's say. Okay, fast moves by two places and finally encounters null, then this loop is going to end, right? So that can also be a reason to break this loop. So we will check. So we will check if we have a cycle or not. If not has cycle, return null. Why not has cycle? See, if our loop breaks by encountering a null value, that means we don't have a cycle. So in that case, our has cycle variable will remain as false. So if not has cycle, then that means we don't have a cycle. In that case, we return a null. Otherwise, if this is not the case, that means we have a cycle. Our has cycle variable is true, right? So in that case, we will start from our head. We initialize a new pointer, right? We initialized a new pointer n at our head. So let's just, instead of creating this new pointer, let's initialize our fast to head again. Okay, so while fast is not equals to slow, move fast by one step, and slow by one step. Okay, at the end, return fast or slow, any one of them, right? What did we see here? We began from here and we began from this meeting point. We moved them by one step, move them by one step, they finally meet, and right where they meet, that is the starting of our cycle. So we return that. Now let's try to run it. Let's submit. Cool. So we already discussed the time and space complexity, right? It's time is big O of n and space is constant, right? So yeah, this is all about this problem. If you like this video, do hit the like button, share this video and subscribe to my channel, and I will see you in the next video. Bye bye.